Alright, so first off, the lecture question today is a little bit different. It's not going to be a coding question, and it's not going to be due at midnight. It's going to be due during lecture, about mid-lecture. To submit this, there's a lecture question link on the course website. If you click this, it'll take you to a Google form where you'll write your submission, where you can write a paragraph text. This does expand, by the way, if you... I have to say that because I always give one-line answers when I use this form. But this does expand. It should be paragraph form. And we'll see what you're going to submit later. Make sure you're logged in with your buffalo.edu email address, or else the form won't accept the submission. That's how I'm knowing that it was you who made that submission. It has to collect your email address so I know it was you. So with that out of the way, let's take a look at some examples. Big brother is watching you. Excuse me. All right, so last time we saw the state pattern, and we saw an example of it with 3 different states. Not too big of an example, but we were just getting the idea of the state pattern down last time. This time, we want to take a look at a larger example. We want to look at the jumper game and how that game is implemented and how it gets some of the features functioning for that game. So like I said, lecture question, it will be due during lecture. We'll talk about that when the time comes. But let's talk about Jumper. Let's revisit this a little bit. It was a 2D, 2-player, vertical scrolling platformer where your goal is to jump up these platforms faster than the other player. And as soon as one player reaches the bottom of the screen, that player game overs, and the other player wins. There's no win state built into the game, so it doesn't say player 2 wins or whatever. You can just keep jumping forever and restart the game if you want to play again. So go climb faster than the other player. We have already seen the physics with this. We'll revisit a little bit of how the physics works with this game. And next week, we'll talk about how the GUI is made, how we're grabbing keyboard inputs, and we'll talk about the MVC architecture. Those 3 topics are for the 2 lectures next week, Monday and Wednesday next week. We'll talk all about that and just see how that's implemented. And then moving forward, we'll start the next lab demo. Lab demo 2 will be to add a GUI to your game in lab, and we'll start working with GUIs after that. So for now, you're given the GUI code. We're not going to really look at that part right now. We've already seen the physics, and what we want to look at today is the player mechanics, the mechanics of the game. So with the physics, just a reminder, it's a lot in one slide, but we've seen all this already. The platforms and the walls both extend static object through the jumper object class. So each platform and walls both extend jumper object extends static object. So every platform and every wall is a static object in this game. We add more functionality on top of static object through inheritance and through polymorphism, but they are static objects. The player is going to extend dynamic object. So the player is a dynamic object. It, of course, can move around. It can have a velocity and move around according to our physics engine. So player extends dynamic object. Walls and platforms extend static object. So every object in our game, everything that is in our game is represented in our physics engine. It can work with our physics engine. So since every object is working with our physics, we're already done with the physics of this game. Everything's done with that. The player is going to be updated each frame. If a player collides with a wall or a platform, the wall and platform are going to take care of how those collisions should be handled. In addition to gravity, everything with our physics is already done. The way this is going to work with the player, though, and the big thing that our physics engine does not do is ever really set the velocity of a dynamic object. The way our physics engine is designed, that's going to be left up to each object independently. So it's the player's responsibility to effectively tell the physics engine or set its own velocity and say, look, this is my intended velocity. I want to move that direction with this magnitude. And then the physics engine takes it from there and says, okay, well, gravity says otherwise, or it detects a collision and maybe a platform says otherwise, maybe a wall says otherwise. So if I walk into a wall, I'm saying my intended direction is to move this way, and when you hit the wall, that velocity is zeroed out by the wall through the collision of the physics engine. So the player is setting its intended velocity, then the physics engine and the static objects take over from there to say whether that intended velocity is valid or not, and then changes that velocity depending on what happened in the world. So physics is done. The one thing we have to do is figure out how the player sets its intended velocity. How is the player going to set that? That's the big thing that we still have to do. For this, I left my good stuff note there. So to set a player's velocity, we're going to look at the player inputs, which are only 3 inputs. A player can either push left, push right, or push the jump button. So just 3 buttons, but we want to add a lot of functionality based on those 3 buttons. So, and this is usually any software we develop. This is typically what we want, a very simple interface for the user, even if we have a lot of complexity in the game itself. So we'll add a lot of complexity here, but still just 3 buttons for the player. The player doesn't really have to think about what complexity is happening under the hood. So player 1, if you play the game, player 1 set up for A, D, and W. Player 2 set up for left, right, and up arrows. So WASD and the arrow keys, the standard controls for 2 players. So we're going to use some states to handle these user inputs accordingly. So what does accordingly mean? Well, let's build these features. And this is when you're on the job and you're ready to develop some software. This is kind of what you're going to get. This is something we'll call a spec sheet in the industry. You're going to get a spec sheet which says all the features that your software must have. Then our goal is to implement all of the features in the spec sheet. So we have this spec sheet for the game, and we have all these features that need to be built into this game. And it's our job to take the spec sheet that the customer gave us. They said, I want all these features in the software I'm paying you to write for me. And it's our job to take those features, design software, and be able to build a working product that the customer can use. The customer can go sell to their customers or use whatever they're going to do with it. But it all starts with a spec sheet or a requirements list that we have to implement. So let's look at the requirements for this game. We're just sitting down talking about a game. Oh, I want to build this game. These are the features it should have, specifically related to the player mechanics. These are the player mechanics that we want in this game. And they're all fairly standard for a 2D platformer, but they might be things, if you've played 2D platformers before, you might not really think about all these things, which is how we want software design. Nobody should be really thinking of the complexity, but they should feel it, and more importantly, they should notice if something's missing out of this list. The jumping mechanics just wouldn't feel right in this case if some of these are missing. Well, debatably. But anyway, let's go through these. So starting off with the easiest, the simplest one that everyone would expect. If I push left, if I'm standing on the ground and I push left, I gotta think which way is left for you. Left, the player should move to the left. If I push right, the player should move to the right. If I push jump, the player should jump. I'm not gonna jump too much in this lecture. But the basic controls, we're of course going to have those controls. Those 3 buttons should have that functionality. That's the basic thing, and if that's all we're building, we want the simplest game ever. That's all the functionality we would build, and we'd be done. But we want to get a little more complexity in there. One thing that's nice to have in a platformer is I want to be able to jump higher if I'm moving instead of standing still. So from a standing start, if somebody jumps, they should not really be able to jump as high as if they were getting a running start, if they're walking and then jumping. It's something that we often have in games, and in real life it kind of makes sense. If you get a running start, you'll be able to get up a little bit higher. Also, if I should have different jump heights. If I push the jump button and I always jump at that same exact height, that's not really realistic. A real person can jump at different heights depending on how much effort they exert when they jump. So we want the feature where the longer you hold the jump button down after jumping, we should be able to jump higher based on that. So if you want to do a little partial jump, you can do that just by tapping the button. If you want to do your full maximum potential jump, you'll hold down that jump button and jump as high as you possibly can. So we want the player to be able to control the height of the jump. If I change speed in mid-air, I think a lot of platformers these days give you full air control, full air speed. But But let's add this feature to our game. If they change directions in midair, they'll go slower than if they originally jump. So if they run and jump and then decide, oh, I want to go the other way, they should go slower after they turn around in midair. We'll allow them to turn around midair, but they have limited control, limited speed based on that. If I'm jumping up through a platform, this one we talked about at length. This is handled by the physics in the static object of the platform. But if they jump up through a platform, they go through it. If they fall down onto a platform, they should land on it. Again, we talked about that one at length so far. We won't really talk about that much in this lecture. If I'm walking, if a player's walking and just walks off an edge, they should start falling after that. They should fall down based on gravity after walking off that edge. And if they reach the bottom of the screen, disable all 3 of their buttons. The player can't do anything after that. So we could do this without states. You can imagine we have quite a bit of different functionality going on there, depending on a lot of different factors. We could do this without states. We could have one player class with 3 button press methods and build everything out from there. We could do that. My guess is that code's going to be hard to follow unless you take some idea of the state pattern and separate that functionality in some way. If you write it all in one class in 3 methods, that code is very likely going to become a huge mess. It's going to be hard to read, hard to follow, hard to maintain if you want to add new features. It's going to be very difficult to do if you're writing everything in one class with lots of if statements, lots of conditionals, and lots of different functionality all in these massive methods that are hard to pick apart. So we're going to skip that idea and go right to the state pattern and see how would we do this using the state pattern to keep our code a bit more organized and a lot easier to follow and significantly easier to add new features. Ideally, adding a new feature after we have a lot of features should be the same amount of work roughly as adding the first feature. Every new feature should be about the same amount of work. That's our goal, and we'll see how that works out with our design. So let's revisit how to design using the state pattern like we did last time. And I broke this into 3 kind of steps. You can do these steps in different order than I have listed here. But we want 3 different things. We want to write our API. So what are the methods that should change behavior as the state changes? What are those methods that are going to change? Those are the methods that I'm going to defer to the state for the functionality instead of building into the player itself and just call the state methods of the respective name whenever it's called on the player. What are those methods? And that's going to define my API when I have my state-based class. Those are the methods that go in that class that'll be extended in the concrete classes. So what are those methods? What states should exist? What are the different states that I should have in this? What are the different states that a player can be in when they're moving around this game? And finally, what are the transitions between those states? When do we transition from one state to another? And this is where we're going to hit that lecture question. So the lecture question in that Google form, I'll give you some time in lecture, at least 5 minutes. I'll play it by ear, see how the discussions are going. You can talk with your neighbors, you can collaborate on this. In the form, I want answers to these questions. What states do you have? What's your API? What are the state transitions? And just type up in paragraph form your idea for the design of the states of the jumper game. And yeah, the answers are kind of out there if you want to read ahead in the slides. I'm not going to stop you. If you want to look at the code, I'm not going to stop you there either. But I will, so after lecture, I'll go through and manually grade all these. So you won't see any scores, of course, right away. But submit the form, and probably by tonight, I'll grade them, I'll look at them all. So I'll give you at least 5 minutes here to discuss and submit that form. What I came up with the state pattern, with programming in general. We're all going to come up with different answers, so if yours wouldn't be the same as this, if you're making different state diagrams, If for your homework you come up with a lot of different states than my solution, that's all perfectly normal. We're going to have different approaches when we apply the same ideas. There's an AI subtext there too. If you have the same ideas and both coded up, it's going to be way different. But I don't want to go down that path right now. So here's what I come up with for the player, all the behavior of the player based on this. So the API, I got seven methods, at least for this design here. If you look at my code, I have a few extra methods, just the way I end up implementing a few things. But 7 methods here. 6 methods for left, right jump, either pressed or released. So I want to capture every time a player pushes the button, and every time that button is released. And I definitely need the release because if a player holds to the left, I want the player to keep moving left. Once they release it, I want that player to stop. The jump height, of course, I want to capture exactly when that jump button was released, so I know how high to jump. And then landing on a platform, depending on the state, it's a little bit different behavior of landing on a platform. Very minor difference. I could probably leave that out of my API, but I'd have to have an if statement somewhere if it's not. The big thing is if I'm in the game over state and I land on a platform, I don't want to transition to the standing state if that's how I have it set up. So I added that to my API just so I can say, even if you land on a platform, you're staying in the game over state in that particular state. But we could do without that and just have the button presses. We could even just have the presses and not the releases, depending on how you want to code it up and how you want to implement everything specifically. But we definitely at least need the 3 button presses. You need that at least in your API because these states are going to behave differently based on the button presses. Which states? I can either be standing, walking, jumping, falling, or in the game over state, where I fall below the screen. So these are the states I came up with where the behavior is going to change based on which state I'm in. These states are going to react differently to the button presses depending on these. And the difference between jumping up, and rising, and falling is if I hit a platform when I'm falling, that should behave a little different. I could probably get rid of that as well and have the platform take care of that. But I do want a little bit different behavior between rising and falling. Sorry, I forgot. The rising, I should be cognizant of the up button released method. That should behave a little bit differently when rising rather than falling. And finally, the state transitions. A lot of these are what we'd expect, but I'll go through them one at a time. If I'm standing and I press left or right, I should transition into the walking state. If I'm walking and left or right is released, I should go back to the standing state. If I'm walking or standing and I hit the jump button, I should go into that jumping or rising state. When I land, I haven't even mentioned falling yet, but if I'm falling and I land on a platform, I should transition to the standing state. If I'm walking and I walk off the edge of a platform, I should transition into the falling state. If I'm jumping and I reach the apex of the jump, one of the few cases in this game where we'll actually kind of need a conditional. It's hard to do that one without a conditional by adding new states, but we'll check. If I'm at the apex, start falling. But when we hit the apex of a jump, we'll transition to the falling state. And no matter what state we're in, if we reach the bottom of the screen, it's game over. Zero out all the buttons, don't have any functionality after that. So between these last 3 slides, well, that's a lot of text. This is where, once the states become more complex like this, where we're really going to see the benefit of a state diagram. So let's visualize this and see what's actually happening with that state diagram. What are we doing there? And it's going to look something like this. We have our 5 states and how we transition between each state. So all those transitions in the previous slide, all the states 2 slides ago, they're all captured in this one visual diagram. And for the calculator homework, you definitely should be drawing a state diagram. Draw all the different states of your calculator that your calculator could be in, and draw the transitions between them. You should have something similar to this for your calculator. Definitely draw out your state diagram. This homework is much more of a design homework than anything you've coded so far, at least for your academic career. Draw it out, go to the drawing board, and draw a lot of diagrams, tweak them as you need before you go to the code. It's highly, highly recommended. So for the jumper, this is what our state diagram looks like. It's all the same information as the previous 2 slides, but in a nice graphical form, showing all those transitions. Now when I go to my code, I'll create a class for each one of these states. I'll create an abstract or trait class for the state itself, defining the API, all the methods that can be called from the state, all the functionality that's deferred to the state and not handled by the player. And I'm going to implement each one of these, extend my state, and implement the API. First thing I'm going to do, if it's me, I'm going to go to each one of these methods in the state diagram, and I'm going to draw all my transitions, add all the transitions in. Once I have the states and the transitions, I have this whole diagram in my code. Now I don't have to think about the state transitions or the state or the jumper game itself. I don't have to think about any of that anymore. I'm just going to go to each one of these classes and implement each of the API methods. Okay, if I'm in the rising state and somebody hits the left button, what should happen? Implement that method. It's a quick, short answer. Okay, if I'm already moving in that direction, I should just keep moving in that direction. If I'm changing direction, I need to go in that direction but at a slower speed because I'm in the air. If I'm in the walking state and somebody hits the jump button, well, my state transition is already going to be there. I'm going to move to the rising state. And my z velocity should be set to my walking z velocity for my jump height for the z direction. And for our purposes here, our standing and walking jump height are set based on the velocity, my initial velocity for that jump. And physics will take it from there. All we need to do is set that initial z velocity. Physics engine will take care of it with the gravity. It'll come up with my jump arc. It'll be a nice, beautiful parabola. Everything will be great with that. And so on. I just go to each one of these states and implement whatever behavior the API should have in that state. And then the game over state. In the game over state, I'm going to override every API method in my state class and just set it equal to open brace, close brace. Just nothing, no functionality, nothing should happen in the game over state. And then if you look through the code, I have one extra API method for is dead. It returns true. Game over state returns true. All other states return false. That's just so the game can check if the player is in that game over state or not. So when we're implementing these states, there's two pairs of two states in particular, the rising and falling states and the walking and standing states, that have a lot of functionality in common. So of course we're going to have some state class that defines our API, and we're going to extend that state class for all of our states. But when we have these cases where we have two or more states that share a lot of functionality, we got to think back to last Monday's lecture where we saw inheritance for the first time. We said we have these two classes, they have a lot of similar functionality. Let's factor out the common functionality and put that in one base class and extend it twice. So, and we did that for inanimate objects with ball and health potion. Here we want to use that same concept, that same idea, but say, okay, whether I'm standing or walking, a lot of the functionality is the same. Let's factor out that functionality, create another class that we're going to call on-ground, for all my on-ground states, which are going to have the same jumping behavior, roughly the same jumping behavior and things like that, and walking behavior. And we're going to implement all the common functionality in that, and then extend state from on-ground, and then extend on-ground for standing and walking. So I can leverage inheritance and polymorphism, not really polymorphism here, but I can leverage inheritance to limit how much I'm duplicating my code and how much extra work I'm doing. And we can do the same things that we saw with inanimate object. If there's new functionality that we want to add to every single state where the player is on the ground, we'll add it to that on-ground class. Now it's shared between standing, walking. Maybe we want to add a running class too. We're going to add that functionality to on-ground. Maybe we want to add ducking like we did for Monday's lecture question. We'll add that to on-ground and have all those states have that similar functionality, and then add whatever specific to that specific state in that class. Same with the two in-air methods. Rising and falling are going to behave mostly the same. In fact, with the, no, I changed it, sorry. In fact, most of the functionality with rising and falling will be the same. So let's create an in-air class If the player's in the air, they're going to behave this way, and then just put all of the in-air functionality there. Then only the things that are different between rising and falling, which isn't much, not much different between those two, that functionality we're going to put only in those two states. So we can take advantage of inheritance to organize and limit our code, maximize our code reuse, and keep our code a bit more organized and easier to expand with these kind of intermediate states. Then on ground and in air would be abstract classes. Even if state is a trait with no functionality, we'll have some functionality in on ground and in air. Those will be abstract classes. So, should pause for a bit. Any questions at this point? I'm throwing quite a bit at you there. Anyone good on that? There's got to be at least some questions. Let's see if chat's got any. So if somebody's falling and they press right before they land, so in my state diagram, it's kind of implied here, with falling and then landing on a platform, I'm always going to transition to standing. But if the player is holding left or right, on the very next frame, they're going to transition back into the walking state. So it's only one frame that they'll be in the standing state. Nobody's ever going to notice that. You're going to be able to do a land and run without the player ever noticing. So that's handled in the state diagram implicitly. We could add that explicitly to our code, but you're gaining one extra frame of the proper functionality. We're gonna be okay with that. But there are ways you could get past that and have that one frame be fine as well. No other questions? Yes.
So when you're expanding on ground, have it extend state, have state things that on ground, all together, how inherit.
So how do we? So with the state diagram, we have, say, falling extend in air, and in air extend state. So falling will have all of the functionality of in air and all of the functionality of state, all in one class. And we can do that by having our inheritance tree like this. So in air is going to extend my state object that stores my API, add any functionality that is exactly the same for rising or falling. And then for my rising and falling classes, I only extend in air. So rising extends in air, but in air, since in air already extended player state, then rising and falling will both be, through the in air class, will both be player states. They'll both be of that class. So then in my player state class, I still get all this functionality, which some of the updating I ended up putting in here. It's just the easiest way to do it. My API methods. And for some of these, I actually do have default behavior, so this has to be an abstract class. And then in the player class, I have one state of type state variable, of type player state. I'm initializing this to a standing state, and since standing extends on ground and on ground extends player state, standing is of type player state, so I can store it in that variable. Does that answer your question? So all of these classes, all these states do, through another state or directly, in the case of game over, do extend the state, whatever my base state class is. I call the player state in the code, that state, base state class. So I can have one variable of type state or player state in the code, and I can set it equal to any one of these states. So my player can be in any one of these 5 different states. So one of the big things I advertise with the state pattern, it's easy to expand your code, it's easy to add new functionality. So let's do that, let's add some more functionality. We have our 5 states, and I want to add a double jump. I want to add a double jump to the game. If you're not familiar familiar with games, double jump is while you're in mid-air, you can jump one additional time. So if I jump, I'm in the air, I can jump one more time, but I can't jump again after that. So, oops. I was going to open the game and show you, but you have to take my word for it. A double jump one time in the air, but then if you hit the jump button again, it should be disabled. So if we're not using the state pattern, or we're just using poor design overall, this could get pretty difficult if our code is a handful of methods with big if blocks, with else if, checking multiple conditions and all this stuff. If we're checking all that in a few big methods, this could get pretty difficult. With our state pattern, no problem at all. We're just going to add a little bit of functionality to some existing states, then add a few new states to handle this double jump. So if I'm either rising or falling and I push the jump button, so we could even add this in the in-air class. We don't do that, you'll see in a minute why. But in rising and falling, we can say if you hit the jump button, you jump again. You set your z velocity back to the jump velocity. I believe I used the standing jump velocity for the double jump, but you could have it as a third different velocity, whatever you want. And we'll add a few more states. Since we have different states you can be in, you can either be rising after a double jump or falling after a double jump, where the jump should be disabled. We have different functionality for the jump button, so we're going to add new states, 2 new states for this, whether we're rising or falling after the jump button was pressed. And then these states, we're just going to extend, so rising after double jump, just extend rising. We already have all the functionality we need. We're just going to extend rising and disable the jump button. So these states are very simple. We're just going to extend the existing functionality and have the jump button do nothing. And then our transitions, we'll add a few more state transitions in there. I'll talk about this last. So our state diagram, just the way I organized it on the slide looks a little messy, but we added these 2 new states and transitions to be able to get to those new states. And each one of these states is just rising after double jump, extends rising, override, jump press to be empty, nothing, do nothing. So not much work to add this new functionality, and we get a double jump in our game. So we and then extend those classes to override that jump button. Now we could have done this with an if statement in those classes. We could have just said, if we've already jumped, or if we haven't jumped yet, or used our double jump, jump, and then used our double jump to true, so we can't do it again. We could certainly do this, but one, if we do this a lot, if we use this approach often, our code can get out of hand quick. And if we want to add different functionality, like maybe there's something that you want to do after a double jump and not before, it's going to be a bit more of a mess to be able to add that. But more to the point, what if your professor gives you an assignment where you can't use any control flow? Well, we can't use this method, so you're kind of stuck. If you have some functionality that should only work once, maybe a decimal button, you might need more states for that. After you press that button, move to another state where that functionality is disabled. The lecture questions, of course, are already done. Highly, highly recommended to start your calculator. You have everything you need and more for the calculator. Give that a go. If you want to practice with what we talked about today, try adding a running state to jumper. After you're in the walking state for a while, you can run and then jump higher when you're in the running state. Okay, see you all Friday.